Good morning, my lovely 13s. Right, buddies, today we get to talk about a really exciting topic in mechanics. It's still in our moments unit about all the twisting forces and the balancing of forces and all that good stuff. And the topic today, my buddies, is called tilting. So if you put the title of tilting, that will be brilliant. So basically, I found these really cool pictures online that I wanted to show you. Oh, I should have researched if anyone was hurt in these pictures. I didn't actually research that before I put them on. So let's just hope that nobody was injured in these pictures. Right, buddies. So here we go. Tilting, my buddies. Essentially, if you've got stuff that's balanced, so say for instance this little picture down here, the beam is on two supports on C and D, or in real life where you've just got something that's overhanging something, you get to a certain point where enough of the mass is beyond where essentially you get the center of mass past the spot that's supporting it. So for instance, the front of this bus that's going over this bridge, it looks like, the front of the bus is further ahead. The center of mass of the bus is actually off of the bridge itself. Because of that, the bus itself is going to act a bit like the rods do and all of these things, or the beams, or whatever the devil they're called, and it's going to want to spin off the edge, and it's because of moments that it's doing that, okay? So it's going to have a spinning force where that is treated as the pivot, where it's tipping off the edge, and it's going to spin off the edge. Same deal here with the partial force guy. He's only just got probably his front tires off the edge, but more of the weight of his van would have been in the front of the van because that's where the engine is. So it's enough to lift the back wheels completely off the ground, even though he's only just a little bit off of the edge. And it's kind of like a center of mass question meets a moments question, and that's quite cool anyway. So yeah, that's what we're going to talk about, is tilting. How exciting. Cool. So let's check it out. First question, my buddies, is this one here. What we've got is a uniform beam, and let's do it. Uniform beam of mass 45 kilograms and length 16 meters rests horizontally on support C and D. AC is that, CD is that. Now it says when a child stands at A, the beam is, and this is the key part here, on the point of tilting. That means, my lovelies, it's not actively spinning, okay? It's not going in circles like that, what I'm showing you with my mouse, but if there's like literally even just one feather were to land on the child in this question, it would tip over, it would start spinning. So the point of tipping, or the point of tilting, means it's about to tilt, but it hasn't done so yet. It puts it in what's called unstable equilibrium, but you don't need to know that either. But yeah, that's what it means. Tilting about C, and the question that we're actually asked to figure out is find the mass of the child. Okay, you guys are going to be happy with today's lesson. I think it's not nearly so bad as the other stuff that we've done. My goal is to get this last topic, teach you this last topic that we're doing right now, and then we are going to do a lesson of really hard practice next lesson. Cool, so let's go and do it. This is good practice. What do we have to do every single time, my buddies? That's right! You have to draw the picture, my folks, so let's do it. Okay. So I'm going to draw my beam, but I'm going to draw it in 2D to remind me that it has mass. And here we go. It's got support C, which is there. And it's got support D, which is there. C and D. This is A, and this is B. And it's got a bunch of distances on it, which I should also include. So the distances are 5 meters. I'm essentially copying the picture above, but you have to copy it as well, so may as well copy it with you. 9 meters is there, and 2 meters to the edge. Okay, now here we go. It says, or well, first things first, it's a uniform beam. So tell me a force. What force do we have on it? That's right, buddies. It has a weight, and because it's uniform, the weight of the beam, which I'm going to call WB, will be directly in the middle, so that'll be 4.5 meters in. So 4.5, no, it won't be. How long is the beam in total? 9 and 5, 7, 16. It's 16 in total. So that is 8 meters in, my buddies. Cool. 8 meters. 8 meters. Okay, from there to there. Okay, what other forces are acting on it? Well, yeah, you've got the two reaction forces. There's a reaction force at C, which I'm going to call RC. And is there a reaction force at D? Well, yeah, it's a support. There's a reaction force at D as well. Cool, cool, cool. Now it says a child stands at A, so there's going to be a kid here. The kid, we don't know how big he is, so we're going to call him M, but he stood exactly at A, so his weight is going to be down here. So we'll call that WK for the weight of the kid. Okay, now ready? It looks like a normal old question. We're asked to find the mass of the child. And it looks like a normal old question, but there's one extra trick to it, my buddies. It says that the beam is on the point of tilting about C. So if the child wasn't there, this thing would be absolutely as we've drawn it in the picture, supported by these two normal contact forces. The RC is holding it up, the RD is holding it up. Both of them are balancing out the weight of the kid and the weight of the beam. So that's what's happening, okay? That's the scenario. But if it's on the point of tilting about C, that means that this kid is stood in just such a way that if he were to jiggle, if he were to like bounce his body up and down, the whole thing is going to go whoosh and tilt up that way. Get me, my buddies? If that's what the case is. And not only that, because it says the point of tipping, even if, say, a drop of rain landed on the kid's head, it'd be enough to tip it over. So we're at the point of tipping it over. Okay. As it starts to tilt, and now it's not going to tilt, but in theory it could start to tilt. As it starts to tilt, buddies, what do you notice about the contact force at D? Well, yeah, if you said that contact force is actually going to go, you're absolutely right. Okay, it's going to lose its contact because as it starts to spin, this part's going to lift up. If it's not touching, there's not a normal contact force because contact forces are for touching and it's not actually going to be touching at the instant of tipping. And guess what, buddies? That's the end of the whole question. So, how exciting. The question is find the mass of the child. Now you can do the rest like normal, buddies. We're after the mass of the child, so we need this. That's going to be linked to WK. So step one, we got to figure out where we're going to hinge. Where do you want to hinge? There's a really good spot to choose. Well, definitely here at C. 100% hinge at C. Hinge at C. And the reason why we're going to pick that is because we don't actually know what the contact force is. I mean, we could, but we don't, and so we don't want to. So, yeah, let's not bother finding that, so we'll just hinge at C. Which means, buddies, straight up normal. Your anti-clockwise moments are going to equal your clockwise moments. Which of these forces is going to go anti-clockwise? Well, it's the weight of the kid. So we have the weight of the kid, and the kid is 5 meters from the hinge. What's making it go clockwise? Well, it's going to be the weight of the beam that's making it go clockwise. And that is going to be at a distance of, oh, here we go. It's going to be 8 so this is 8, that's 5, this is going to be 3 meters. Got me, buddies? From this 8, 8 take away 5 is 3. So that's 3 meters, and that's at a distance of 3 meters. Well, we're laughing now. The weight of the kid is going to be, well, it's the mass of the kid, so let's just call MK for mass of the kid, G, times 5, so I'm going to put the 5 in front even. And the weight of the beam is going to be 3, and it's going to be the mass of the beam times by G. Not only, this question's ace, look, G's go, because they're common to both sides, and here we go. That means that it's just going to be 5 times the mass of the kid is going to equal 3, and the beam was 45 times 45, and just in your calculator or in your head, oh yeah, we could do it in the head. 45 divided by 5 is 9 times 3 is 27. 27 kilograms. Cool. And there you have it, my buddies. I hope that that's right anyway. Yeah, 9 times 3, 27. Yeah, happy days. And that's it. So these questions aren't actually too much harder. The only skill that you needed to know then was just that if something's on the point of tilting, it just means that it's not going to have a contact on the other force, on the other support. Cool. So with that in mind, let's just see if you can do this one all by yourselves. This one is harder, but I'll bet you probably have your head around it enough to try to solve. So I'm going to do it with you, but I'm going to say if you want to go ahead and try it on your own first, go, pause, pause, go. Okay, and you're back, or you wanted to do it with me. Here we go. So this one's not got a picture, which is ace, because we'll just be able to draw a picture. Non-uniform rod. Okay, so, ooh, that's a keyword. Non-uniform this time. Is of length 10 and weight 40 newtons. That's nice, it's in newtons. It's suspended from a pair of light cables. Okay, so it's not supported at the bottom, but held up at C and D, where AC is that and BD is that. When a weight of 25 newtons is hung from A, the rod is on the point of rotating, which is the same as tilting, okay? So it's not spinning yet, but it's getting ready to. Now the question is, find the distance of the center of mass of the rod from A. So we want to know the distance of the center of mass from A. Boom. Here we go. Let's draw it out, buddies. So we have our rod, drawing it in 2D, so it reminds me that it has a mass, because I have to do that, otherwise I always forget. So there we go. Okay, it's called AB, the rod, it says, AB. It's of length 10 meters in total. So let's grab the green one out and do that in 10 meters. In total is how long our rod is. Okay, its weight is 40 newtons, but it's non-uniform, so I can't put that in yet. Light cables are attached at C and D, where A to C is 3. So we have a cable here, 3 meters in. Cool. And B to D is, and then B to D is 2. So that's basically what it's saying. So this is 3 meters. This is 2 meters. And yeah, that's all we got, I think. And the weight of 25 newtons is hung from A. Okay, so let's get our forces on then, buddies. So let's get some weights and stuff on. Well, it says something's hung from A, so right here, I'm going to call it W of the weight at A. I'm going to call it WA for the weight at A. Oh, I forgot to label the letters as well. It said that they're attached at C and D, so that's C and D, the letters. Now there's some forces here. There's actually an upward pulling force at C, okay? That's from that there. Well, it's not a reaction force, or it's not a normal contact force, but it's actually a tension if it's in a string. So there's a tension up there, there's a tension at C, and there's also potentially a tension at D, so I'm going to put that in as well, TD. And the only other thing is that it says that the beam itself has a weight of 40. Now it says it's hung from A and it's at the point of rotating. Okay, which of these two strings are going to go slack first? If something's hung from here, which string is going to go slack? The one that's at C or the one that's at D? That's it, buddies. It's actually the one that's at D. So this TD force, this tension that's at D, isn't actually there, my buddies. Oh, God. The string is still there, though. Yeah, so the tension that's there isn't actually there anymore, okay? That tension force is actually gone, because if it were allowed to rotate like that, this thing is just going to go all loose, right, as it rotates around. So, yeah, there's no tension there. For sure, we also need to know, we don't know where the center of mass is, but where is it definitely? Could the center of mass be between A and C? Well, definitely not, because it would definitely spin if it was there. Could the center of mass be between C and D? Well, yeah, absolutely it could be between C and D, because it's very likely to be, because D is going to go slack. It's probably not on the other side of D. It would be quite a heavy force pulling down on A for it to cancel out D. So it's very likely our center of mass is here, but at the same time, it makes no odds at all if we guess where that is wrong. The only thing that would matter if we said it was between A and C, which it clearly isn't. Cool. We want to know the distance of that from A, so we'll call that X. And boom, we're flying again, my buddies. This is just as the others then. There's a really good spot to hinge. Where are we going to hinge on this one? And for sure we're hinging because we have to get x, which is a distance. So we don't want to use forces, we want to use moments. Hinge at C, clearly, because we don't know what TC is, do we? We don't know what the tension of that string is. So we put the hinge there, then the distance to the string is 0, which cancels out that force, which means we can do our anti-clockwise equaling our clockwise, my buddies. So which one's going anti-clockwise first? Well, it's the weight at A. The weight at A was 25 newtons, and it's at a distance to C of 3. What's causing it to go clockwise? What's the weight of B, my buddies? The weight of B, though, was given as 40. Actually, that's tricky. Oh, I thought this was an easy question. It's not too bad, but it's not easy, because what's the distance actually to get from here to here? Well, actually, it's measured from C, so it's not X. It's not the X that I said it was. So we're going to have to introduce something else here. What's this going to be? What's this distance that I've got in blue here? Well, yeah, it's actually X take 3, isn't it? If this whole distance is X, and that's 3, that's X take 3. Oh, I love it when a bit of algebra sneaks in. So we're good. There we go. X take 3 is the distance from it to the hinge. Cool. So 75 equals 40. X take away 120. So I'm going to do the calculator just to make sure I don't make a mistake. 75 plus 120 equals, divided by 40 equals, and we've got 4.875. Cool beans, my buddies. That is the distance of the center of mass all the way from A. Okay, my buddies. So that's the distance from A because we labeled our X up there. Alternatively, if you had read ahead in the question, like I suppose didn't do, you could have labeled this distance here, the blue part, you could have labeled X, but then you just have had to add 3 to the answer. But one way or the other, it's all good. Cool beans? Hopefully not too hard of a topic today. I don't think it's as bad as the last couple lessons. And here we go, my buddies, for our second to final lesson. This is what I'm going to get you guys to do. I hope that's not a Dudley's bus. It kind of looks like one a little bit. But anyway, page 184, question 1 to 7, do a mix. And I really want you to concentrate on this section, okay? Now, if you're finding that you're really in the pattern, you're welcome then to move on to page 85, 1 to 12. These are actually the mixed exercises. But next lesson, I'm going to try to get you, as long as it works out in the scheme of work, which I'm sure it will, I'm going to try to get you a lesson that I just find really hard nightmare questions of these about, because moments can be quite tricky. So I'm going to try to purposely seek out horrendous questions for you to try next lesson. But yeah, 1 to 7, first of all, little mix for me. Get bored of those. So you did questions 6 and 7 only, and you're a bit bored, pop on to page 85 and see how you get on with that. Cool beans? Upload me a picture when you're done, and that's it for me. See you next time. Bye, buddies!